Today's goal of this lecture. In my previous video, I had seen type of singularity. I had seen there are two types of singularity, one isolated singularity and second non-isolated singularity. And isolated singularity are three types: pole, removable singularity and essential singularity. And in my previous video, I had discussed what is the pole and what is the essential singularity. In my previous video, I had discussed function has a isolated singularity, then always there exists Lorentz series expansion, and in Lorentz series expansion, when finite principal part, that means if a minus n not equal to 0 but a minus k equal to 0 for k greater than equal to n plus 1, then this is the pole of order n. And when there exists infinite principal part, then this singularity is essential singularity. Also in my previous video I had seen what is the behavior of pole when function has singularity of pole. Behavior of singularity near pole. If fz is analytic and has a pole of z equal to z0, then modulus of fz always tends to infinity as z tends to z0. Second, if z0 be an isolated singularity of the function fz, then z0 is actually the pole of order n. If and only if fz equal to gz divided by z minus z0 to the power n, where gz is analytic function at z0 and gz0 is not equal to 0. Third, if z0 is isolated singularity of function fz and z0 be the pole of fz of order n, if and only if 1 over fz is analytic and has a 0 of order n. That means if z0 is pole of order n, then 1 over fz has a 0 of order n. In my previous video I had seen this all be the behavior near pole. Today's goal of this lecture, today I will see what is the behavior when essential singularity exists. But at first I will see some example of singularity. First function fz equal to cos z minus 1 over z square. Which type of singularity exists for this function? Cos z means we all of us know 1 minus z square over 2 factorial plus z to the power 4 over 4 factorial minus z to the power 6 over 6 factorial. And cos z minus 1 when minus 1, then cos z minus 1 means this one and this one would be cancelled. So the series would be here 1 over z square and here minus z square over 2 factorial plus z to the power 4 over 4 factorial minus z to the power 6 over 6 factorial, so on. When divided by, since here divided by 1 over z square, so z square would be cancelled. Here would be z square, here would be z to the power 4. So the series would be such type: minus 1 over 2 factorial plus z square over 4 factorial minus z to the power 4 over 6 factorial. That means notice here no negative part of z. And this type of singularity is actually removable singularity. When in Lorentz series expansion there are no negative part, and this is I will discuss in my next video. But today's goal of this lecture, today actually I will see some behavior when isolated essential singularity exists. Next function fz equal to cos z over z to the power 4. Cos z means 1 minus z square over 2 factorial plus z to the power 4 factorial minus so on, divided by 1 over z to the power 4. So the function would be 1 minus 1 over z to the power 4 minus 1 over 2 factorial 1 over z square plus 1 over 4 factorial minus z square over 6 factorial, so on. Here notice, here finitely many negative term of z exist. So this function is pole, and when fz equal to cos 1 over z, then this is equal to 1 minus 1 over 2 factorial times 1 over z square plus 1 over 4 factorial times 1 over z to the power 4 minus 1 over 6 factorial times 1 over z to the power 6, so on. Here infinitely many negative term exist. Notice here finitely many negative term exist of z. That means this is the pole. And since here infinitely many negative part of the z exist, so this is the essential singularity. Okay. That means suppose z0 is the isolated singularity of an analytic function with Lorentz series expansion series k equal to minus infinity to infinity ak z minus z0 to the power k, where 0 greater than absolute value of z minus z0 less than r. Then this singularity is removable if ak equal to 0 for all k less than 0, and poled if there exists capital N, so that a minus n not equal to 0 but ak equal to 0 for all k less than minus n, and this index capital N is the order of the pole. Since here the finitely many negative term exist and highest power of this is 1 over z to the power 4, so this is the pole of order 4. And essential singularity if ak is not equal to 0 for all infinitely many k less than 0. Since here in Lorentz series expansion infinitely many negative power of z exist, so this is the essential singularity. I hope my all viewers have understood this is okay. Oh well. Other behavior near pole which I have not discussed in my previous video. This is a rational function has no singularity other than pole. And why a rational function has no singularity other than pole? Because suppose fz is a rational function, so that it is expressed in the form fz equal to gz over hz, where gz and hz both are polynomial having no factor in the common. That means hz equal to 0, this is actually zeros of hz. That means singularity of fz when hz equal to 0, this is actually zeros of hz. And we all of us know reciprocal of zeros always be the pole. So the zeros of hz are actually pole of 1 upon hz. Singularity of fz are actually the pole, because here fz equal to 1 over hz and 1 over hz equal to 0 means this is actually the pole. So the rational function has no singularity other than pole, only singularity here pole. Now I will see behavior near essential singularity. What is the behavior near essential singularity? Let f be non-constant entire function. Then f is not polynomial if gz equal to f of 1 over z, where z belongs to complex number, has essential singularity at z equal to 0. Then when gz equal to f of 1 over z has a essential singularity, that means f is not polynomial. Other behavior of essential singularity is Cassarity-Oyster's theorem. Cassarity-Oyster's theorem is very interesting theorem. Let A be an essential singularity of the function f. That means at the point A, function has a essential singularity. Then f of b dash ar is dense in whole complex plane for any r greater than 0 with b of ar contain u. That means take any small deleted neighborhood around the point A where A has an essential singularity. Its image would be whole complex plane because its image is dense in C. That means its closure would be whole complex plane. C closure would be whole complex plane. That means image closure would be whole complex plane. That means take any small deleted neighborhood around this essential singularity, but its image always would be whole complex plane. No matter how small neighborhood you will take, its image always would be whole complex plane. And sequentially we can tell, sequentially suppose z0 is an essential singularity of the function f. Then for every w0 belongs to the complex plane, there exists a sequence Zn with Zn goes to Z0 always imply f of Zn goes to W0, and this is true as n goes to infinity. That means the picture would be such type. This is domain and this is codomain. Here W equal to f of z. If we consider W0, then there exists a sequence Zn which converges to Z0, and where at the point Z0 the function has a essential singularity, and f of Zn which converges to, this is f of Zn which converges to W0. This is the Cassarity-Oyster's theorem. That means actually if we consider any deleted neighborhood about this essential singularity, then its image always would be whole complex plane. And another behavior of essential singularity is Big-Picard's theorem, and Big-Picard's theorem is similar to Cassarity-Oyster's theorem. The statement of Big-Picard's theorem is, let Z not be isolated essential singularity of an analytic function. Then f of 0 less than z minus z naught less than epsilon, and this is true for all epsilon. That means any deleted neighborhood around the point z0, always this would be either whole complex plane or complex plane omitted with singleton's point W0. That means take, similar to Cassarity-Oyster's theorem, take any small deleted neighborhood around the point Z0, then its image always would be either whole complex plane or complex plane omitted only one point. This is the Big-Picard's theorem. Later I will say what is the Little Picard's theorem, but Big-Picard's theorem depends on when Big-Picard's theorem useful, when the function has essential singularity. Okay, let's see one example. As for example, Consider fz equal to e to the power 1 over z has an essential singularity at the point z equal to 0. So, by Picard's theorem, for every w naught not equal to 0, there must exist infinitely many zn with zn goes to 0 that imply f of zn equal to w naught. Now pick w naught equal to 1. Then since f of z equal to e to the power 1 over z, so e to the power 1 over z equal to 1, that imply 1 over z equal to 2 pi ni, and this is true for all n belongs to integer. That imply zn equal to 1 over 2 pi ni. Then zn goes to 0 as n goes to infinity. That imply, notice, e to the power 1 over 2 pi I. This is always equal to 1. So, f of zn equal to 1. That means for this point 1, w naught equal to 1, always I will get one sequence. At least one sequence. Actually, there are infinitely many sequences. Such that since this function has singularity at z equal, essential singularity at z equal to 0, such that zn goes to 0, that imply f of zn goes to w naught. Here w naught equal to 1. I hope my all viewers have understood this is clearly. Okay? Well, I will stop here. In my next video, I will discuss the image of entire function. Some image, how look like the image of entire function. But at first I will highly recommend you, please see today's video with pay attention, because behavior near pole, behavior near essential singularity, this is actually very important for higher study also. Okay? See you soon. Stay safe, stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.